by a number of his celebrated works in quantum foundations information, ranging from his works on quantification of entanglement to generation of entanglement by gravitational interaction between macroscopic masses, but as well as by a number of very thoughtful and very instructive books and his writings. And I have been also have been a very deep admirer of his books and writings. They are illuminating and with a refreshing novel perspectives. And I have personally benefited a lot. And because there are many students here and others, I may mention particularly his two books, although they are a bit costly if the institute libraries can get them, they are really certainly worth getting them. One of them is that Introduction to Quantum Information Science, and the other one, particularly, he has also other quite books, but these two books stand out, I think, and another on the modern foundations of quantum optics. And of course, his two delightful popular books, The Decoding Quantum Reality and From Micro to Macro, which I think everyone interested in science should read. So I eagerly look forward to Vlatko's talk today, and I hope it will be certainly, and I'm sure it will be quite an interesting session. And Vlatko has a flair for interaction and for answering questions. So I would encourage and urge the students to be quite free with their questions and comments so that this session is quite an engaging one. Okay, so over to Vlatko now.
Thank you, Dipankar.
Platform is yours.
Thank you very much. Thank you for this lovely introduction. I don't know what to say, actually. I think it's very nice to be invited and that we share this common interest in fundamental issues in physics. The only thing I can say is that I'm sorry I'm not physically there to interact with you, and I do hope that this really will happen in the near future.
So by the way, Vlatko, you have 1 hour time. You have 1 hour time. So
excellent.
Maybe I shall remind you 5 minutes or 10 minutes.
That would be great. That would be great.
10 minutes.
Thank
so
you.
that we
Thanks
have time for this discussions.
That would be great. Anytime. Please ask questions.
Okay.
So let me motivate this talk by saying that it's really exploring a different formulation of quantum physics. My motivation for that actually comes from many directions. I probably don't even have the time to maybe talk about all of these things, but I will mention some of them, and then I'm happy to discuss more others. So as you know, it's for us physicists, it's important to understand any phenomenon in as many different ways as possible. This enriches our understanding of the world, first of all, but secondly, we are always struggling to understand new phenomena. And it could be that if we are failing to understand something, it is because we haven't looked at things that we already understand, possibly in a different way. And that, of course, happened many times in the history of science. So this is a different formulation of quantum mechanics. And we already know that dynamics in quantum mechanics can be phrased in many different ways. We have different pictures in quantum physics, but not just even different pictures. We have all sorts of time symmetric formulations. So this is this point that quantum mechanics is reversible, of course. So you could give the initial condition, and that's normally how we do physics, really, and then you can involve those initial conditions in time. You can do that in many different ways in quantum mechanics, or of course you can give the final condition and you can involve things backwards. You can do half the initial and half final. So those are all the games you can play with reversible evolution. One of the motivations also is to treat space and time somehow within the same formalism. So rather than give the initial state at a given fixed time, like I said, and then evolve it in time, it seems necessary frequently, even in a non-relativistic theory. I will only talk about non-relativistic theory, although many things that I've been doing are actually strongly influenced by relativistic, by quantum field theory, ultimately. And the tricks that we have to perform there in order to be able to quantize certain things. And of course, this final point is really the main point that I'm making here. You know, if someone says, why are you doing this new formulation? What's the point of that? Then really, the motivation ultimately is that we don't know whether a different perspective will actually help us in the future. And that's maybe something I want to mention now, because, for instance, one of these motivations could simply come from relativity, but relativity where you are talking about smaller and smaller distances and shorter intervals, for instance. So, you know, in relativity, the key thing is to classify all events into space-like, time-like, and null. Once you've given this, for every two events, you've effectively specified the metric. So you've specified everything there is to specify. But if you believe that there could be some quantum uncertainty at play when you're talking about very small intervals, and this is what I'm trying to somehow depict on this diagram. So I have an event 1 and event 2, but there is some fuzziness about these events. So you may not be able to tell whether these events are really null or maybe time-like or maybe space-like, simply because there is a certain fuzziness that could be quantum mechanical if we believe that that's what it means to quantize space-time ultimately. So this could be one of the motivations. How do we take into account correlations between events when we don't want to even commit ourselves to these events being space-like, time-like, or null? And that could be one motivation for what I want to do. And now I want to basically give you some examples to show you what this entails. So I call it a pseudo-density because it is like a density matrix. I'm putting all the correlations into this matrix, but the pseudo part indicates that when you write this correlation in time, and that's the example I want to give you, you will actually arrive at an entity that's not necessarily positive. So this is a Hermitian operator that may have, and I will give you that example immediately, negative eigenvalues. So what I have in mind is the following very simple experiment. I have a qubit at one time, and I measure this qubit in the usual Pauli basis, X, Y, or Z. Then I wait a little bit, and this waiting you can think of as a simple identity transformation. I'm not assuming any evolution. You could add the evolution. It's very easy to phrase it in that way as well. So I make a measurement, and then I make another measurement at a later time, also in the X, Y, or Z basis. And then I repeat this on an ensemble, just as though you were using two spatial qubits and you were doing the full tomography on them. You want to reconstruct the full state of two quantum bits. And now you're using instead one quantum bit, but you are measuring this quantum bit at two different instances in time. And it's clear that in this very simple example, if I first measure X on this qubit, I will either get +1 or -1 eigenstate of X. But the next time I measure, I will, of course, have to get exactly the same result because nothing happened between these two measurements, according to my assumption. So the XX correlations in time, and likewise YY or ZZ or any other correlation in time, will be 100%. If I measure +X initially, I will, of course, have to measure +X finally. If I measure +Y initially, I will have to get +Y at the next measurement, and the same for Z. Now, if you pretend that this is a normal density matrix of 2 qubits, even though you're measuring a single qubit at 2 different instances in time. So this is this picture where the qubit comes completely maximally mixed. So I don't even need to use any coherence in this initial state. I'm even assuming it's completely randomized, if you like, completely incoherent. And then I proceed with this ensemble of incoherent qubits to make these 2 measurements, one at T1 and the other one at T2. And then I construct a density, what should look like a density matrix under normal circumstances. What you will get is simply identity. 1/4 is the normalization, so that the trace of this object still equals to 1. So it's normalized, interestingly enough. However, the signature of the correlations is plus for XX, plus for YY, and plus for ZZ. This is what would happen if you pretended that a single qubit measured at 2 different times is actually like 2 spatially separated qubits, and you just proceed to write down the state of these 2. And now you notice that this actually state is not a physically allowed state in space. So basically what I'm saying here is that it has a negative eigenvalue. In fact, what it looks like is it looks like a state that you would obtain, and this is important for maybe people in the field of quantum information. It looks like a legitimate state. So this is one of the triplet states here, one of the Bell states, 0, 0, plus 1, 1. If you applied this operation partial transpose to check whether the state is entangled or not, the Perez-Horodetsky criterion, you would actually end up with this previous pseudo-density matrix. So it's a pseudo-density because one of the eigenvalues happens to be negative. And it's very easy to check this. If you diagonalize this object, it's a 4x4 matrix, it really is very simple, you will get eigenvalues plus a half, plus a half, plus a half, and minus a half. And of course, if you want to interpret these diagonal elements as probabilities, you will run into the difficulty of having negative probabilities. And so what does that mean? And of course, what this means, we know what this means in time. It means that different measurements in time don't, of course, commute with one another, unlike measurements on spatially separated qubits, which completely commute. So the lesson, very briefly, is that I'm trying to now think of different instances in time as different Hilbert spaces, and I'm trying to treat space-time correlations in a completely unified way. So the way I would describe 2 spatial qubits, I'm now ascribing the state in exactly the same manner to the same qubit measured twice or multiple times. You can generalize this completely in time. The price to pay, like I said, is that there is an occurrence of a negative eigenvalue there. And that really tells you, of course, that things in time, different measurements in time don't necessarily commute. Of course, X and Y and Z do not. They are the maximally non-commuting, if you like, set of observables. And I think if you look at this paper, I don't want to kind of bore you too much about the structure of this. You can actually characterize all the possible physical states, all possible pseudo-density matrices that can arise from 2 measurements in time on a single system. And I think this paper here that I'm citing gives you that. I want to talk a little bit about this. It's almost like a side comment, but it is very much related to entanglement in time, if you like. So the way I came to these pseudo-density matrices is that I realized, and this, of course, is something that Leggett and Garg have also done, is that in fact, Bell's inequalities could actually be phrased in time. You could be measuring a single qubit multiple times, and then you could construct an inequality that looks very much like the Leggett, like the Bell inequality, which is called the Leggett-Garg inequality. which leads you to conclude that there is an analog to entanglement in space, and I think I called it entanglement in time. So different measurements in time on the same system could be thought of entangled in exactly the same way, to the same degree, by the way, the √2, if you like, in terms of Bell's inequalities, as qubits in space. And this gave me the idea that maybe we should describe space-time in general in exactly the same way and ascribe a density matrix to temporal correlations as well. And like I said, it becomes a pseudo-density because you cannot maintain the positivity. Now, there is this, this sounds very relativistic in a way, because even though I'm talking about completely non-relativistic quantum mechanics, and it sounds relativistic because it looks as though this minus sign, the negative eigenvalue, comes from treating the time as an imaginary component of the 4 vector. If I think relativistically of x, y, and z as the spatial coordinates and t as the temporal coordinate, then we know that the interval in special relativity is actually the interval that I wrote down, and it looks as though the time really should be multiplied by an I, by the square root of -1, which is how you get this minus sign between the spatial and the temporal components. One interesting consequence of that, so now I want to link it to quantum somehow. One interesting consequence of that is that you violate the triangle inequality in special relativity. So if you look at the distance between 2 events and the distance between 2 other events, this could be longer or shorter than the distance between the first and the last event. So actually the triangle inequality in relativity is frequently violated. And all the paradoxes, all the apparent paradoxes, there are no paradoxes with relativity as we know, but all the apparent paradoxes like the twin paradox, or anything we talk about, the contraction between different observers, boils down to the fact that this interval is not a proper distance. It doesn't satisfy the triangle inequality. So going around, so to speak, can be shorter than going directly between events. Now, as most of you know, in quantum mechanics, when we write the Schrödinger equation down, we frequently think of also the Schrödinger equation as a diffusion equation of sorts. It's not really diffusion because we know it's a deterministic equation. But actually, you could think of it as a diffusion in imaginary time, whatever this may mean. So somehow that seems again similar, that both relativity and quantum mechanics seem to want to treat time differently, almost like the imaginary component in this 4 vector in space-time, if you like. And of course, you can immediately ask yourself, wait a second, does that mean that there is a violation of the triangle inequality in time? And the answer is yes. In fact, that is the Leggett-Gard inequality. That exactly is the temporal Bell inequality. So the parallels are very interesting. I don't quite know what this is really telling us, and whether something more interesting can come out of it. But it seems already a very interesting statement to me. I'm giving you a general temporal Bell inequality now. You make n measurements at one instant on time and n measurements at the other instant of time. And then you look at this is of course again done on an ensemble where you just choose your measurements at the first instance, then you choose your measurements at the second instance, you exhaust all possible measurements that you need to do, and then you take the expected value, just as you would with Bell's inequalities. And now what's interesting is that the sum of all of these distances, the distance between A1 measurement, A is the first instance of time, B is the second instance of time. I'm treating them really like 2 subsystems, A and B. So if I go and look at all of these distances, A1 to B1, B1 to A2, and I go in a kind of chain-like way, I construct a chain of these quantities, then what happens in quantum mechanics is that this left-hand side can actually be made to go to zero as close as possible, as a function of the number of measurements that I make, whereas the right-hand side can ultimately end up being a unit distance. Namely, unit distance in my logic here just means there are two orthogonal states. So the
Vlatko, can you
zero,
please,
yes.
Vlatko, can you please explain this inequality again a bit? The symbols there,
Yes.
slowly. Yeah.
Yes, let me explain it again. I have two measurements in time, and at the first measurement, I have a choice between measurements A1, A2, A3, AN. So there are n measurements that you can make. You can think of them as measurements on the block sphere. They could be as close to one another as possible. And in fact, I'm drawing measurements that are very, very close. So Z, then I tilt the Z direction a little bit, tilt it a bit more, and so on. And these B measurements are exactly the same measurements, spaced out in the same way, but they are made at a later time. So at the first instance in time, I choose one of the A measurements. At the second instance in time, I choose one of the B measurements. And then I continue down my ensemble of identically
But the two consecutive measurements are of the same
two consecutive
variable.
measurements.
Of the same variable. Of the same variable, not necessarily.
No, not the same variable, slightly rotated.
Slightly rotated.
That's it. So the blue basis in my picture is the A basis, and the red basis would be the B basis. Just slightly
so that slight rotation, that will determine the inequality, how it is violated or not.
Exactly right, because this distance scales as 1 over n squared, which is what I wrote down.
Yes.
And that's because it's really the angle, it's the sine of the small angle, sine squared of the small angle between these elements. And there are two n of these, so on the order of n of these terms here, which means that the whole left-hand side will go as n times 1 over n squared. It will go as 1 over n. And when n becomes large, this will basically go to 0, the left-hand side. The right-hand side, I will look at the distance between the first measurement in A and the last measurement on B, which are basically orthogonal measurements in this picture, if you like, and they will give you the distance of 1 if you normalize it in the way that I'm normalizing. So somehow it's interesting that each of these measurements, neighboring measurements, are arbitrarily close to one another. You can make the angle arbitrarily small by increasing the number of measurements, but when you add them all up, you actually get a finite distance. In fact, you get the largest distance you can get under this norm. And this is really a generalization of Bell's inequalities, but I'm presenting them in time. You could do the same on 2 qubits, and you would get the same result, I should say. You could literally measure many closely spaced measurements on 1 qubit, and then many close measurements on the other qubit, and you would get exactly the same inequality. So it's very interesting.
So this inequality is given in your earlier cited paper, or is it?
No, it's coming up. I will mention it. Not yet. Sorry. Okay. Yes, I think it's coming up. In fact, excellent point, because I want to explain that. So what we did is we asked a colleague of mine, Marco Genovese, in Turin, in Italy, to do this kind of temporal measurements. I think he works with the usual down-converted photons. So this is just a nice image of a crystal where you shine some light and you generate entangled photons in polarization. And then you make a sequence of these measurements on them. And so I want to describe to you what it is that they've been doing in general. And I think the reference to the paper will come in a second. So here is now, I want to generalize it a little bit now, because all I talked about is 2 instances in time. I want to show you how to write a pseudo-density matrix when you're combining space and time together. So this now corresponds to one of the experiments that have been done. So basically, I have two qubits, one at x1 and the other one at x2. And you can measure them at some point, call it at some time t1, just as you would for the standard correlations, Bell's inequalities. But now I want to measure the second qubit for the second time at time t2. And this now, in my representation, will be like a state of 3 qubits, which is interesting. So basically, there will be qubit 1 here, qubit 2 here, and they are real physical qubits. And then qubit 3 at T2 will actually be one of the 2 qubits which is measured for the second time. And these statistics I will combine into a state of 3 qubits. And that's the interesting thing, because now I'm mixing both space and time. I want to show that it's possible to cover all of the events in the universe with a pseudo-density matrix. I want to really write the pseudo-density matrix of space-time, if you like. That's kind of the vision here. And you can see you can roughly see what I'm doing here, that I have a normalized state of 3 qubits, as you would write it down with Pauli operators. I'm assuming now I'm doing Pauli measurements. You can generalize it if you want to, but Pauli measurements suffice. And the first two are simply your singlet state between the 2 qubits. They have a minus, minus, minus sign, minus XX, minus YY, and minus ZZ. They're anti-correlated singlet states. The other two are these weirdly correlated qubits in time, where they actually have the plus signature. So if you measure x2 here and you measure it later, you have to get the same result because nothing happened between these two. So here, when you measure x, you will get the same value of x here. When you measure y, you will get the same value. So it's plus, plus, plus. And then there will be a 3-point correlation, which will involve measuring x here, and x here, and then y, 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 and then z, z, z. You can see that if these are the only things that happen, that there is no evolution, there's no dynamics in between at all, just the state preparation and the measurements, you can actually come up with a pseudo-density matrix of this type. And the beautiful thing about this is that it works exactly the same way as a normal density matrix. If you now want to say, wait a second, what I want to know is just the state of x1 and x2. I want to trace out this third qubit. You can do that. It's the same operation of trace. And if you trace that out, you will get exactly the singlet state density matrix between these two. You can equally well trace a spatial qubit out and get the pseudo-density matrix for 2 temporal qubits, which will have this plus, plus, plus sign. So it's kind of interesting that the machinery, the mathematics of these pseudo-density matrices is identical to the mathematics that we use on ordinary density matrices. They're perfectly consistent with all the subsystems described consistently. The only thing is, I keep emphasizing, it's a pseudo. It's not a positive operator. Not necessarily. Sometimes it may be, of course. And here is a general. This is the reference where actually we did some experiments with NMR on that, and I won't tell you too much about it. But this slide is simply to show you that you can write a pseudo-density matrix for n events. Some of them could be spatial, some of them could be temporal. It could be a mixture of these. And you write down the pseudo-density matrix the same way that you would write a normal spatial density matrix of n qubits. And this just tells you that it's a Hermitian unit trace operator. You can trace subsystems out, get the correct consistent reduced pseudo-density matrices and all of that. And in red, I'm saying the only thing is that there are negative eigenvalues. And that's the interesting thing. So let me now talk about an inverted question from this. And this, I think, is interesting to me as well. If I'm given the pseudo-density matrix of n points, n events, could I actually reconstruct space-time from that? That's now the the interesting question, in the sense that could I tell you which correlations? That's how I started, by motivating it by saying, if I have two events, I want to know whether they are space-like or time-like. Could I tell that within this formulation? And the answer is kind of yes and no, in the sense that there is a sufficient condition, and that's what I'm saying here, that the negativity of eigenvalues signals the presence of temporal correlations. But in fact, if your eigenvalues are always positive, it could be that this comes from both spatial and temporal measurements. So somehow there is not a unique way of distilling space-time out of this. And maybe this is okay, like I said, because you may have situations in practice where you really cannot even fundamentally tell whether the correlations that you are measuring are really come from spatially separated or temporally separated events. Maybe that loses its meaning completely. So let me give you this example now, which to me looks very, very interesting as well. So I have three measurements in time now. I'm generalizing this to three measurements in time. I measure the same qubit at T1, then I wait, measure it at T2, then I wait, measure it at T3. But what I'm doing now is between these two waiting times, I'm introducing a channel that's depolarizing in all three directions equally. This is a channel which reduces the x, y, and z values by an equal amount. This sigma operator is simply the xx plus yy plus zz operator between 1 and 2, 2 and 3, and 1 and 3, and 1, 2, and 3. So this 1, 2, and 3 sigma is xxx plus yyy plus zzz. And now what's interesting when I send this through a channel is that in a certain regime, even though all three measurements are temporal, there is a regime where each two states, 1, 2, 1, 3, and 2, 3, are perfectly valid density matrices. They are positive operators, while the whole thing is actually a pseudo-density matrix. So that's very interesting because it reminds me, and it probably will remind many of you, again, of Bell's inequalities, of contextuality in quantum mechanics. So basically, every two event can be ascribed a probability distribution, but the whole collection cannot be derived from a probability distribution. That's a restatement of Bell's inequalities, if you like, contextuality, the quantum contextuality. Every reduced state can be simulated classically, but the totality cannot. It requires a quantum wave function. The same is true in time. Every two-point pseudo-density matrix requires only a physical state to represent it, but altogether, they cannot be put together to come from a genuine positive quantum state, which to me signals correlations in time. That's exactly how you can talk about time within this formulation. Sorry, while I talk, I realize that there are questions, and maybe I can, if it's appropriate, I can answer them now. So Colin Benjamin says, why do you need two qubits to be in two different Hilbert spaces? Why not both in the same Hilbert space? So I think the answer here is that I'm really trying to treat different instances in time as different Hilbert spaces. I'm imposing the same Hilbert space structure that you would do on two qubits. Now I'm pretending that measurements in time also come from different Hilbert spaces. And we know this is not the case in ordinary quantum mechanics. And that's why this is the intuition why when we do that, we are going to get something funny. And the funny thing is the negative eigenvalue. So that's the whole point. I'm breaking quantum mechanics by trying to treat time in exactly the same way as space. And what happens is this. But it's still beautifully consistent. I'm trying to now develop this logic, and actually I can do the whole of quantum mechanics in this way. That's the beauty. So I need two Hilbert spaces for two times because I'm encoding temporal correlations in exactly the same way as spatial correlations. That's the motivation.
But Vlatko, there is
yes.
a point there, maybe reckoned with, that these two spaces, although they're commuting spaces, the operators in them are not commuting, no, because the time measurements.
That's it.
That non-commutativity part of that argument, how it is linked to negative eigenvalue, that is it.
That is exactly it. That's what gives you the negative eigenvalue.
But that does not, one cannot see this transparently, means how that non-commutativity gives rise to negative eigenvalues.
I think you would simply, the way to see it probably is to take the formula trace of your pseudo-density operator times whatever observables you are measuring. And you can put them together. You can put x tensor y and then y tensor x, and you will see that you will not get the same results.
So the inequality you derived, that for n, that inequality also is crucially related to that non-commutativity, because that depends on how different are the measurements.
Yes, that's exactly right. Because even when you tilt it by a little bit, your measurements are already non-commutative.
Non-commutative. So by how much it is non-commutative, if you can quantify that in some way, that can be linked to the violation of the inequality.
That is exactly it.
And that is different from the spatial case. Spatial separation, it is not like that.
Exactly right. Exactly right.
Okay. So that is
and then, sorry, I just noticed now as I was replying to one of the questions that there was a previous question. I'm sorry I ignored it. I didn't realize it. The question is by Arum, who says, can pseudo-density matrix be written for teleportation? It's a brilliant question, actually. And I'm coming to that too. I will now formulate dynamics in quantum mechanics as a sequence of teleportations in time. So I'm going to use the pseudo-density matrix as a cluster state, as a highly entangled state of temporal qubits. And then I'm going to be talking about dynamics as a teleportation sequence through this kind of network. And it's an alternative formulation of quantum mechanics. It gives you the same results. I mean, I constructed it exactly to give you the same results, but it's a beautiful question. Because what I'm advocating now is that we take the notion of temporal entanglement as seriously as spatial entanglement. And then your question is very natural. Given that we have teleportation in space, what would it mean to teleport in time? And what it would mean is it would give you the standard dynamics that we get in quantum mechanics. It's an excellent question. So actually, let me see how far I can get, because I think I'm getting to the experiments that I want to talk to you about. But let me mention this also interesting point. This is really a summary of the discussion so far. So now I'm going to phrase this temporal contextuality that we discussed, namely the fact that measurements in time do not commute with one another, unlike measurements between spatially distinct qubits, which of course completely can be done in any arbitrary fashion without affecting the result. That's the whole point. So I want to talk about how you could argue for the existence of time from these kind of correlations. And it's a summary of what I said before, that we observe marginals, meaning states between events 1 and 2, 2 and 3, 3 and 4, and so on, which are completely characterized by a legitimate positive normal density matrices. However, we notice that the whole thing together as one state cannot be described by a density matrix. It has to be described by a pseudo-density matrix. And that forces us immediately to acknowledge the existence of time. That's kind of that's kind of an argument for time, purely based on these kind of correlations between different. Sorry, there is a question. I keep switching now back and forth, and they may be good to. So the question here is, how is entanglement in time related to pseudo-density matrix formulation? Exactly the same way as entanglement in space is related to the density matrix of qubits. So you can show, so the state that I write down, the pseudo-density matrix, looks like a maximally entangled state. It's got XX, YY, and ZZ maximally correlated, but with the wrong sign, with plus, plus, plus sign. That's not possible in space. In space, you can only have maximally anti-correlated state. That's a singlet state. But there is no spatial maximally correlated state. That's very interesting in its own right, by the way. In time, it's the exact opposite. What exists are perfectly correlated states in time. And if you apply the same trace expected value on temporal measurements, you would violate Bell inequality or whatever is your signature of entanglement in time. You can map the structure one by one between density matrices, pseudo-density matrices, and measurements in space and measurements in time. So entanglement in time is directly encoded in the pseudo-density matrix, directly. That is the point, actually, to encode all possible correlations in time. Okay.
Can I interrupt you
Of
here?
course, of course,
I have a question. See, the question is, when you have space and time, you have related symmetries and then conservation laws. So do you have implications for that? I mean, given your density matrix formulation, I mean, at least in the standard way, we know that, the time translation invariance has its own implications. Similarly, space translation invariance. Now, if you mix it up, there are things which are symmetries of Lorentz, like commute with the Lorentz boost or generators, for example. Do you have similar things here encoded into it?
No, I haven't considered. Yes, good question. I haven't considered this at all yet. All I'm considering is really how to encode different measurements that I make both in space and time so far. I haven't imposed any additional symmetries. And I think this is a very important point, because I think this should also be done at some point. So if I really want to write a pseudo-density for the whole space-time, then I must acknowledge, I agree with you, the underlying symmetry of this space-time. I haven't done that at all. All I'm doing is I'm imagining measurements that are done on different spatial locations and different times, and I'm encoding it as a density matrix. That's all I've done so far.
I understand.
It's a very important point.
Thank you.
And I think that's the next steps. So let me just say another interesting thing, which I think will motivate some of the things that I think are nice. Let me check. I hope I have enough time to tell you about this. So basically,
yes, we have 20 minutes more, at least.
Brilliant. So basically, one of the features of spatial entanglement is this famous monogamy of entanglement, that if two subsystems are maximally entangled to one another, they cannot be entangled to anything else. In time, this no longer works. You can have events 1 and 2 maximally entangled, and 2 and 3 maximally entangled according to this logic at the same time, so to speak. It's funny to put it like that because these are different time measurements, but you know what I mean. So basically, one way of expressing that is that you can do this kind of Bell-like inequality in time, and you can monogamy, ordinary monogamy, if these subsystems 1, 2, and 3 were spatial qubits, 3 different qubits, then we know that the Bell violation between 1 and 2 plus this Bell operator between 1 and 3 cannot exceed 4. So that means if one of them is above 2, the other one cannot be above 2. That's just a mathematical way of encoding monogamy. However, in pseudo-density matrix and the state that I presented before, where you have two spatially entangled systems and one of them is measured twice in time, can perfectly violate both spatial and temporal Bell inequality. And this is kind of obvious because temporal correlations behave differently, if you like, to spatial correlations. And in fact, what you can have is the maximum violation of both of them simultaneously. So 1 and 2 could give you 2 root 2, and 1 and 3 could give you 2 root 2, or 2 and 3 could give you 2 root 2, whichever order you take there. So it's basically as though you violated Bell's inequalities twice. And again, I'm showing you this picture, how this was done by Dow converted photons. Maybe I don't want to spend too much time here, but the crux of this is to generate an entangled pair of photons, do one kind of measurement on one of them, and then do 2 measurements in time, one and then the other one on the other qubit, if you like. And so it's a bit like quantum state tomography, but state tomography that's done in a little bit of a weird way, because on one of these qubits, you've repeated the measurements at 2 different times, which is not what you would normally do in an ordinary state tomography. You would just measure one qubit, the other qubit, and stop and repeat and get the statistics. Here, you measure one qubit, the other qubit, wait, and measure again the other qubit. And you have 3 qubit pseudo-density matrix. 2 of the qubits are spatial, and the other qubit, the third qubit, is actually a temporal version of one of the spatial. You can do a 4 qubit as well. You can measure both of them at a later time. I wanted to do it deliberately asymmetrically to show you that even this works. You can do 4 qubits. 2 qubits are spatial, and each of them is measured twice. That gives you a 4 qubit pseudo-density matrix.
So here it looks like qubit 2 and 3 measurements are of the same variable or different variables. It is
in general, it should be different variables.
Different.
Here it looks the same. You're right.
Same.
It should be different. It must be different. You're
different.
right. It should be different. If you don't do anything between the 2 measurements, then of course you will see that different variables are completely uncorrelated. So if you measure X and then Y, you will get no correlation. And YX, so only the cross correlations, if you like, all vanish in this context. And the only surviving correlations are really X, X, Y, Y, and Z, Z. But this is, of course, an accident, so to speak, of the fact that we don't do anything in between these 2 measurements. If there was an evolution happening, a rotation in between, then, of course, you would expect X, Y to also be possibly correlated. So it could get more complicated and all of this can be described. But you're right. Here it so happens that the only surviving correlations are when you measure the same observable. It's just an accident. It's just the simplicity of the experiment. And now what we thought, and this is maybe the fun part, I don't know if I take this seriously because I don't even understand whether this is possible in general.
Vlatko, someone wants
yes.
to ask you a question by raising hand. Mridul Dixit.
Let me see.
Mridul
I'm
Dixit.
very happy.
Yes, Mridul.
Excellent. I'm ready.
Mridul.
Oh,
yeah, he raised his hand.
yes, please ask me.
Mridul, you please ask your question. No, he's not asking.
That's okay. Maybe
okay.
as I go along, we can return.
Okay, maybe he will ask later. Okay.
So now there is an interesting apparent paradox again when people talk about time-like loops, closed or open time-like loops, where you have the possibility. We don't know if this is true in our space-time, where you have the possibility that one of the qubits undergoes a kind of loop-like motion in time, like a time travel, and comes back to an earlier time. People have investigated this because we know that we have some of these weird space-times that contain these closed time-like loops, where you keep basically doing the same thing over and over again, which kind of looks a bit like time travel. I think it's of course debatable whether this really is true, whether this is possible, and so on. But one of the paradoxes, apparently, that people link to this is the violation of the monogamy of entanglement, and that's what this picture is trying to depict. So the qubit Q1 and Q2 are initially maximally entangled, and then qubit Q2 goes backwards in time, so to speak. It enters this closed time-like loop, comes back, and ends up being qubit 3, which is just simply an earlier copy of qubit 2. And now, when you read some of this literature, like I said, it's not clear that we should take any of this seriously, because we don't really know whether any such possibilities exist really in our universe. But let's entertain the idea that they do, that they did, right? So now what people say is that this kind of arrangement is impossible because you would violate monogamy of entanglement. Why? Because the initial entanglement between Q1 and Q2 would now have to exist also between Q1 and Q3 at the same time, because Q3 is the earlier version of Q2. So now it looks like we have 3 qubits. One is just a qubit that didn't go through this time-like loop, and the other one went back in time, thereby creating 2 copies of itself, each of which now has to be entangled to Q1. And then people say, but this is impossible. It violates monogamy of entanglement. And I think what we did is to show that this is not true, because what you should really be thinking is that these 2, Q2 and Q3, are the same qubit at 2 different times. And then, like I said, if you think of this as a pseudo-density matrix of 3 qubits, 2 of them are spatial, Q1 and Q2, but Q3 is just a temporal version of Q2, then there is absolutely no limitation on monogamy of entanglement. You can have a maximum entanglement between any 2 of these 3 qubits. That's the whole point of mixing spatial and temporal entanglement. So we did kind of, these are just the pseudo-density matrices that arise here. This is like the, you know, the mixture of these singlet and anti-singlet states, if you like. And in fact, our colleagues in, so this is just the statement that you could actually violate monogamy in space and time if you mix space and time. And in fact, here are the results on, again, I don't want to bore you with this. This was really done by my colleague, Fabrizio, who is in Marco Genovese's group. And I think these are the tomographic results of him reconstructing various elements of this pseudo-density matrix by simply making Pauli measurements, x, 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 y, and so on, all of the possible combinations that you need for all the 27, I guess, 3 times 3 times 3. And I think all of these plots are showing you really, I guess, the high fidelity. I think that the paper is cited here. If you're really interested to read more about this, how this is done, then it's sitting in this paper in Nature Communication. So these are really all the results there, the fidelity between all of these, and then finally putting it together, all the correlations, and showing that this violation of the Bell inequality, and I'm sorry I called it B originally, but I think they labeled it as C, the correlations, if you like. C between 1 and 2 plus 2 and 3 exceeds number 4. As we said, you could have both of these simultaneously violating the respective Bell inequality, and then basically repeated measurements on these. And you can see that basically there is no contradiction. I mean, this is obvious. It's just really a very simple proof of principle experiment that's kind of equivalent to Bell's inequalities, but with one repeated measurement, if you like, in time, and no evolution between these measurements. And now I think this goes to one of the questions. Maybe this is one of the last things that I will say, and then we can discuss it a bit more. It was the question earlier, asking whether you can teleport. Can you use this pseudo-density matrix to teleport in time? And the answer is yes. And here is a state at time t1, the pseudo-density matrix at time t2, let's say, and t3. You could think of 2 actually as the time 1, if you like. It doesn't matter. And what I'm trying to do now is I'm trying to teleport the state from t1 through this state at t2 all the way to the state at t3. And you can do that. You can use exactly the same mathematics by making these kind of projections onto these pseudo-densities. So I've decomposed it as pseudo-density matrices on 1 and 2 now, and there are 4 of them, each correlated to a different state at a later time, just as you would do in a teleportation. So at a later time, you will get either the state or a state rotated by X, Y, or Z, depending on what kind of pseudo-density you had between 1 and 2. So indeed, if you have the pseudo-density matrix in time, you can actually think of the physical evolution of your system as undergoing a sequence of teleportations between these instances in time. Now, of course, this is only a mathematical analogy in the sense that we cannot execute the teleportation protocol here. So we can't really measure simultaneously instances 1 and 2 and project the state onto the instance 3. That doesn't make any sense because they're not happening at the same time. But mathematically speaking, it does make sense to think of the physical evolution simply as a sequence of operation on this kind of pseudo-density matrix. It's a curiosity. I haven't been able to do anything more interesting with this, but it seems to me that even this kind of analogy, this part of the analogy works perfectly well. And in fact, you can actually talk about any evolution in this case. You can implement any CP map between different instances in time. And here I'm just presenting a pseudo-density matrix, which kind of acts on the X, Y, and Z values in a way that it decoheres and it shrinks them by a certain amount, eta X, eta Y, and eta Z. And you can construct all of this. And there is a beautiful analogy between this, of course, and the SU2, the basically representation of the Lorentz group, which kind of works in more or less the same way. So when you think about the dynamics here in the pseudo-density matrix between 2 different instances in time, you can map that perfectly well onto a Lorentz transformation between 2 different reference frames that somehow reflect these components X, Y, and Z of your pseudo-density matrix. And I'm listing here people who have speculated. I guess they've all realized something like this in their own different way, who have kind of tried to exploit these mathematical analogies between relativistic formulations and quantum formulation. And I think we go back to probably David Bohm. Penrose has done a lot on spinners, twisters. Weizsäcker, of course, had his John Wheeler, eat from bit, and all of that. So somehow this to me looks very beautiful, that we can package, even though, like I said, all I'm doing is completely non-relativistic. I haven't included any symmetry whatsoever in my formulation. It looks as though the mathematics of these, for some reason, it could be an accident as well, is actually very similar. So here is the paper.
Can I interrupt once again? Sorry.
Of course.
So do you have a notion of time-like separated and space-like separated events in this context?
That's the point.
Okay, that's the point. Okay.
No, not at all. In fact, I put all the correlations as though they come from the spatial correlations. I'm just thinking of different times, and different spaces are different Hilbert spaces. You have as many subsystems as the measurements you make. That's it. And then the question is, if I don't tell you whether my measurements are space-like or time-like, can you distill that out of the density of the pseudo-density matrix? That's the way I'm putting the question. The other way around, which is interesting.
Okay, thank you.
So not at all. No, thanks for asking the question. It's good to ask as we go along. So I'm almost going to conclude here. Actually, the teleportation, and I think including these measurements of the temporal violation of Bell inequalities, are sitting in this Science Advances paper. This also a collaboration with Chiara, Maletto, myself, and the INRIM group of Genovese. And I think there is this extra paper that I cited if you want to read a bit more about this temporal machinery of correlations. But I think most of the experimental results on what I discussed on the last few slides are really sitting.
And also that basic inequality. Hello.
Yes.
Yes. So this also discusses the basic inequality, its basis that you indicated for n.
That is exactly it. This contains the two-time measurement and the Bell inequality in time. Yes.
From the basic principles. Okay. So that is yet to be published. That Science Advances.
No, this is sorry. This was good question. Maybe last year.
Okay. So the exact reference is not here. So we can search for.
It's either 21 or 2020. Actually, good question. Okay. But I think it's last year.
Last year. So the first author is Marletto. And
that's it. I think it's really Chiara and myself suggesting these theoretical ideas, and the rest of the authors are the members of the Genovese group who have actually been involved in implementing this experiment.
Okay.
So there are probably two experiments. One was the one that I cited earlier in Nature Communications, which was about these two spatial and one temporal measurement. And this one is about 3 temporal measurements and the construction of these Bell-like inequalities in time as well. So both of these papers, I think, would be useful to look at experiment. Okay, so let me maybe just in the view of time, just to maybe give some time for further discussions. I'm going to skip a few things. Like I said, there are many interesting things to be said here, but I want to leave you with this thought. Again, I think this is really just for fun. I'm not sure that this kind of thinking is required in the context of black holes and information loss. But another area that we frequently read about is the fact that entanglement monogamy may be violated when black holes emit radiation. So there is this picture which is almost like an artist's impression. It's not clear whether a physicist should take any of this seriously, obviously, because we don't have the theory of quantum gravity. But there is kind of this idea that when you have entangled pairs generated on the surface of the black hole and one of the pairs falling in, there are some suggestions that actually after some time you may get a violation of the monogamy of entanglement, because some of these incoming and some of these outgoing particles, if you like, will have to be simultaneously maximally entangled to each other. So like I said, I don't actually know. Probably if you ask me to bet on it, I think this kind of thinking is completely wrong. I don't think there's probably any paradox when it comes to black hole information. There's no information loss, and I think probably the whole thing can be explained unitarily. That's my personal feeling. However, what I want to say is that when you go through some of this mathematics, it looks very suggestive, because you could again think of the infalling particle as having 2 instances in time of itself. There is one before the falling into the black hole and one after the falling into a black hole. And if you really think of this as a temporally correlated object with a pseudo-density matrix, then again, describing this situation is no problem at all. And one shouldn't expect that monogamy is obeyed at all, simply because there is a maximum entanglement between spatial particles, but there is also a maximum temporal correlation between the particle and itself at 2 different instances in time. So somehow you can model some of these simple protocols, not just in these spacetimes with closed loops, if you like, but you can also model them in some other situations like black holes and black holes radiating and so on. And that's something that we speculate. Like I want to, of course, be completely open about it, that this is a big speculation. And like I said, I'm not even sure that there is any paradox there in the first place. Probably I would say there isn't. But I think another way of thinking about it is simply to combine spatial and temporal correlations and show that there are no problems there at all. So the final concluding slide, and I think please ask me more questions if you have about any of these aspects. The idea really is to treat time instances like modes in space, ultimately, spatial modes. And I've only talked about qubits, because already for qubits, you have to get used to this idea, and it's not simple to switch from the spatial to the temporal domain. But what I want to say is that if you want to now do this for the field theory in general, for continuum, you can actually use harmonic oscillators and measure them at different points in time and construct a pseudo-density matrix of any system of any dimensionality, including infinite or continuous variables, as we call them. And then there is this interesting thing about how to characterize these correlations in time, because as soon as I tell you that correlations in time arise from the same entity as correlations in space, and I think one of the questions was very related to this, you could now say, well, wait a second, I use some kind of mutual information to quantify correlations in space. Could I use some mutual information in time? And there are all sorts of interesting ideas how to actually conclude things that are relevant for quantum information, things like channel capacity and all sorts of communication protocols by using this kind of pseudo-density matrix. And then the final thing I want to mention, because I started motivating my talk by talking about different formulations of quantum mechanics. And what we've been curious, this is the most recent thing, and I can't really tell you much more than what I'm going to say now. But what we want to do is relate this formulation to the two-state formalism of Aharonov. So this is the formalism where you've given the initial state and the final state, then evolve initial state forward in time, involve the final state backward in time, and characterize the state in the middle by the signals from the past and the future. This is, again, a trick that's been used many times in physics, even in classical physics, as some of you might know. And now what we're thinking is that we can actually relate this to pseudo-density matrices to even define a pseudo-density matrix at a single instance in time. So far, I was only talking about two instances or more, but it seems to me you can even combine this with other ideas and really come up with a full formulation that's equivalent to these other more maybe unusual formulations of quantum mechanics. And I'm going to stop here and thank you very much for your attention.
Okay, thank you very much, Vlatko, for, as usual, wonderfully stimulating talk. I'm sure there are many questions. So please go ahead with the questions. So I think
maybe can I go ahead and ask?
Yes,
I have a few. Okay, so I think one question which comes to my mind is you got into this black hole paradox and so on, and very curious. Yeah. This is going on my mind. So what if you the two measurement times? So you're essentially thinking of two space-time points on which you did the measurement, and what if they are connected by a wormhole? So is that the point? So does that kind of
what do you mean by connected by one point?
Wormhole.
Oh, wormhole connection. Sorry, I misunderstood. Yes, I didn't think. No, not at all. I think it's I didn't think about wormholes at all. I was just thinking of this flip of the sign in the metric when you cross the Schwarzschild radius in a black hole. Somehow, basically, what happens to be time for the outside observers, it switches to space in the inside of the black hole. And that very much reminds me of this partial transposition, which is the trick that you use to get from an ordinary density matrix into a pseudo-density matrix. But I didn't think about wormholes, whether this could be done in any physical way of this kind.
Because I remember, when they were trying to, part of the solution to this paradox of this entanglement being sustained over long distances is to say that there is a wormhole connecting them between the
Yes.
pairs. And then
Yes.
it immediately comes to your mind that what if I try to interpret your thing in the same way? So that's one question. The other question is more of an experimental thing. I know this, that in NMR, people have tried measuring this OTOC, the out of time order correlation function. And then, what they do is they go back in time. They pretend they're going back in time by simply changing the sign of the Hamiltonian. So does it anyway help in kind of getting some access to whatever you're talking about in an
I
experiment,
think
or
so.
it doesn't?
Excellent. No, it's an excellent point. It does actually. And part of some of the papers, this actually was a big interest of one of the students of mine, who ended up working on continuous variable systems. And I think she was exploring the connections exactly between pseudo-densities and these kind of measurements that are out of time correlators, if you like, to call them like that. So I think the connections exist there because these measurements are very similar. And I think you can even probably map the two structures into one another. It's a very good point. I don't think we have the full theory of that, but it seems to me that this is an important point as well.
Okay, thanks a lot.
Is Mridul Dixit still around? Hello.
Hi.
Hi. So, or Shreyas raised hand. No, there is no one there. So, any question? Anyone else?
Hello.
Hello. So, Vlatko, so just a query. Yes. So that mutual information in time, the point you raised, and you talked about channel capacity, others. Can you elaborate a bit on that? Because that is an interesting question in itself, but for any temporal.
I agree with you.
Yes.
I agree with you. I didn't say much about it because one thing maybe to be said is that there is an immediate apparent problem with this formulation that you have to overcome, which is why I think it's an interesting question. Because remember, when we are given a normal density matrix for 2 qubits, let's say, then what you tend to do is calculate the reduced entropies of each qubit, and then you subtract the total entropy of the 2 qubits, and that tells you basically how correlated they are. The more correlated they are, the smaller the total entropy. And of course, when the things are entangled, you get the maximum. Each of the reductions gives you 1 unit of entropy, and the total entropy is 0, and that's the maximum you can get. The problem with temporal correlations is that you cannot employ the same machinery simply because you've got this negative eigenvalue in time. So we somehow have to think a little bit more carefully. We can't just take the entropy of the reduced systems. That will be okay, because reduced systems are still qubits, valid states in the states that I presented. But if you want the total state, the entropy, if you're using rho log rho, the p log p, and your p, one of the p's will end up being a negative number, and then you have to worry about what this means in terms of entropy. So there is an immediate issue there, which is why we thought that this was curious. And the question was, is there some other entropic way of quantifying these things in time and overcoming this difficulty of negative probabilities?
So in order to use such temporal correlations for applications like communication complexity,
yes,
and to define channel capacity and so on, there is a problem of ensuring inner consistency.
That's it. I think that the measures that are traditionally based on entropic measures seem not to be at least exactly not immediately applicable.
Immediately adequate. So that is a challenging issue.
That is a challenge, and you may say, well, why don't you take the absolute value, right, and then somehow combine it, eliminate the negativity. So there are some possible avenues in that
and
direction,
use the negativity argue.
That's it. That's it. That's it. That's it.
Okay. So,
Poonam has a question, Dipankar.
yes, yes.
Yeah, yeah. So I have a question. Probably you covered it. I missed the initial part of your talk. Where is this information of space and time not being on equal footing hidden in your pseudo-density matrix formalism? If you could.
Yes, a good point, actually. So when I say that they're on an equal footing, what I mean is that I encode the measurements in space and the measurements in time in exactly the same way. Each of them is allocated a separate Hilbert space. So if I make 3 measurements in space and 4 measurements in time, this will be like 7-qubit system for me. So in that sense, they're treated in the same way. But where they end up being different, and we discussed this a little bit, is that the temporal measurements give you this funny negative eigenvalue. So they cannot be fully like the spatial measurements, because the measurements in time do not commute. And
That's
so
right.
this negativity will reveal the difference between space-time already at this non-relativistic level. That's the interesting thing. So
And,
somehow
it
I'm trying the same formalism, but the outcomes will be different for space and time.
Okay. Yeah.
Mridul, would you like to ask a question because your hand is raised, Mridul?
So Vlatko, in
Yes.
Leggett-Kirk kind of stuff, the aspect of macro-realism is emphasized, because when you make the assumption, the non-invasiveness, in your derivation of the inequality temporal, this non-invasiveness of measurement is also assumed.
Not really. That's also an excellent point. That I don't have any assumptions of macro realism.
That means also no assumption of non-invasiveness of measurement due to the first measurement. Not at all.
Absolutely right. It's very nice that you are raising this point. Not at all.
Not at all. So this is an important distinction with the
Yes.
Leggett-Kirk type of approach.
Correct. Correct.
And your inequality is derived on the assumption of, so what are the assumptions? So basically it is in the quantum machinery.
That's it. We apply the fully projective, maximally, if you like, distinguishing measurements. So okay. we are in the opposite limit. We don't do kind of measurements.
Okay, so projective strong measurements.
Projective strong measurements. That's it.
And then you derive some correlation in it.
And you still get this exactly.
Those inequalities. So the violation of those inequalities, what would you tell us? So
again, I think it tells us that these temporal measurements have the same kind of correlation, if you like, the strength, just the strength of the correlation as the measurements in space, which is very interesting.
So the violation, that inequality, violation of that inequality is a measure of that strength.
It's the measure of that strength. And I think I noticed in one of the questions just now that someone was asking about going beyond. Could you go beyond the 2√2 violation of Bell? And I think it's very interesting that in time you also cannot. So it's really interesting that the maximum you can get in time is exactly the same as what you can get in space. So quantum mechanics limits you in the same way.
But there it is because of violation of realism and locality and all those things. And in Leggett-Kirk you have macro realism. So here, what is the counterpart?
I think the counterpart is the simple non-commutativity of these measurements. It really comes directly from this geometry. of the measurements.
So it is the
So
non-commutativity which is restricting.
That's it. That's exactly
so
it.
it's a different
exactly
way
it.
of looking in that sense,
Exactly
with no
that.
input of realism here.
No.
So
That's excellent. What you, yeah,
that
exactly,
should be made perhaps clear at the beginning, because
that is true.
Because you alluded to Legedgar
yes,
as an analogy.
Yes, Legedgar has this completely different purpose.
Different
I
way.
agree.
So
it's a completely different way.
It's not analogous to Legedgar. It
no,
is complementary.
It comes down to, you're right, it comes down to the kind of more or less same inequality, but it's with very different assumptions.
Assumptions.
That's
yes.
it.
So
that's it.
Very, very
Thank you.
Point. Okay.
Excellent,
okay.
excellent.
This makes me very curious. Can I follow up this question?
Yes, sure.
Just no, you just said that the inequality for Bell and Legedgar, the bounds are same. And why did you say? I thought the Luder's bound is the bound for a spin half, which is like 1.5. On the other hand, on the with the Legedgar, you get a 1.5 bound, and there you get a 2√2. In some sense, you said they are in equal footing. In that sense, you created them. I mean, just in terms of number, they are not equal. So I'm just curious.
Yeah, I have to say that I'm very careless with terminology. I think Leggett and Garg, for God knows what reason, have used only 3 measurements instead of 4. So I think they went with the original Bell inequality. But what they should have done, and this is what I think I did and should be done, and it's better, is to have 4 measurements to construct a CHSH like inequality in time. So I'm actually being kind to them in some sense and attributing to them what they didn't do, because I think spiritually they wanted to do that in a way.
Yes.
That's what I have in mind.
I see. Okay.
Yeah, you're right. You're right. They only had 3 measurements.
In fact, many of the experimental tests of Legedgar have used 4-time measurements, and many of
that's it.
Papers,
that is it. And then it's 2√2. That's it. So I think many people interpret it my way.
And in fact, in our papers also we have used
makes sense.
4-time measurements.
And then you don't talk about probably like no signaling in time and so on and so forth, because your time and space are mixed up. No, I mean, yes, right. So
great question. I think no signaling, of course, if you take it in this direct way, there is no signaling in time. It's exactly when we signal in
yes.
However, I think what Dipankar raised is this non-invasiveness of your measurements. That would be the equivalent somehow, because what you're really trying to say is that in classical physics, making the first measurement has no effect on the second measurement. They're completely independent of one another. So if you want this no signaling in time, then the equivalent of that is some kind of non-invasiveness. But I'm not assuming anything like that.
Yeah. Okay. Thank you.
It's because I'm dealing with a genuine quantum object. I'm not comparing it with classical physics at all. I just want to formulate quantum mechanics in this way.
So what is interesting, just within quantum mechanics, you are able to define some kind of temporal non-locality, if I may say.
That's it. It's temporal non-locality, if you like to call it like that. That's it.
To spatial.
That's it. Exactly.
Yeah,
that's
like
it.
That. And I also appreciate this point. Very few people realize that within quantum mechanics, you don't have non-locality like Bell non-locality or all these.
Yes. Yes.
Good. So Prashanta, you have comments?
No, I just wanted to, I mean, I'm just enjoying the discussion, and Chiranjeev is here, our colleague, also Chiranjeev Mitra would like to say hello to you.
Yeah, hello. Yeah, you might remember me. I had done some experiments on your PQ inequality and entanglement, specific heat as entanglement witness. So we would look forward to doing some
I love these experiments. Yes, right. Of course. Yeah.
So I would probably like to do some experiment on these also in future.
Yeah, I'm very happy to discuss them more whenever you want. Yeah.
Right. Sure.
Prashanta, I was asking Vlatko if you'd like to visit Calcutta in near future. And he said he would be most interested. So you may consider having him here at the opportunity. And he loves
I'd love
interacting with students and so on.
I'd
and
love
his
that.
lectures.
Yes.
So that would be great. And also, Vlatko, I'd love to interact with you more on this quantum biological stuff, because I'm trying to also do some new work on it. So I would exchange.
That would be great.
Great with you.
Yes.
Yeah, I've been following your works in this area.
Thank you.
No, I would like to add that Vlatko's papers are all over here. Our students follow his papers like crazy. Almost all of your papers are read here. So
thank you.
Thank you.
So Prashanta, I think.
Yeah, I think we can end it.
End it. We had a very very lively session and very instructive discussions. So Vlatko, thanks very much for your effort and the time you have given. We look forward to again interacting with you. Thanks very much.
Thank you.
And
thanks very much,
Prashanta, for giving me this opportunity.
Thank you.
And the organizers of QIQT.
Thank you.
Thank you. Thank you, Vlatko. Thank you, Deepak.
Bye. Take care.
Thank you.